Hello everyone and welcome to this new section in which we're going to look at different strategies of combating overfitting and underfitting. These strategies will include data augmentation, as we could see here, dropout, regularization, early stopping, smaller network usage, hyperparameter tuning, and normalization. Don't forget to subscribe and hit that notification button so you never miss amazing content like this. So far in this course, we've mentioned the terms overfitting and underfitting without really getting in depth to what these two actually mean. Now, for overfitting, we'll consider this plot of the loss versus the number of epochs and then precision versus number of epochs. With the loss versus number of epochs, what we'll generally have when a model overfits something like this. So here we have the validation loss, and that here we have the training loss. So this is just like a general way of looking at this, though this may take different forms. Now that said, as we could see, we have this two sets and their loss versus number of epochs plots. Clearly we could see that the validation and the training set initially start up with a similar pattern. Sometimes you may even have the validation which comes up like this. So you can even have a situation like this where the validation performs even better than the training set initially. But generally, when a model overfits, what we'll have will be this kind of model where at some point the model keeps doing well at the level of the training and starts doing very poorly in the validation set. We could replicate this with the precision epoch. This could be precision, accuracy, recall, or some other metric which we've chosen. And what we could have will be something like this. Obviously, you saw in the practice it isn't always like this, but something in this sense. So you would have this here. You see, you have the training, and then you have the validation right here. So what goes on is your model keeps on doing very well for the training, and then with the validation at some point it starts doing even very, very poorly. And so the danger with this is if you're considering working only with a training set, you may feel like you more epochs or training over more epochs is a good idea because you keep having this great results. Like supposing we have fixed this here and that your training is like say 99%, so you have 99% precision score for on your training data, and you're like, wow, this model will do very well in the real world. But this isn't generally the case because this model actually has been overfitted on your training data. Your model has learned instead to modify its weights based on the training data instead of being able to extract useful information or some intelligence from the data which has been used in training this model. The main cause of overfitting is having a small data set and a large and complex model which contains so many parameters. Now, if a model like say a deep neural network has many parameters and you're giving it a small data set, then obviously it's going to adjust its parameters such that on this small data set it performs exceptionally well. So you may come across a model which has say 99.9% precision or accuracy just because the data you've used to train the model has or was very small. Now in another case, you may have say a moderate sized data set and then not just this kind of model but a very large model. So at the end of the day, we notice that there has to always be a balance between this data set and the model size. So this means that even if you increase the data size and then you also increase the model size, your model may still risk overfitting. To better understand this concept of overfitting, let's take this simple example. Supposing that you have 3 subjects to master at school, let's say math, English, and sports. But when kids get to school, they are only taught mathematics, or they only taught English, or only taught sports. Let's choose, for example, mathematics. So these kids get to school, and from the first year to the last year, they taught only mathematics. It's clear that when you evaluate this kid, or when you pick a kid at random and evaluate that kid in mathematics, the kid will tend to have a better or an above average result in mathematics compared to kids from other schools. But when tested on subjects like English and sports, that may not be the case. And this is because the English and sports weren't taught at school. And so if you are evaluated on only what you were taught, you would tend to have very high scores like this. And then what if we start to evaluate on stuff the kids were not taught? You'll notice that those kids will then start having poorer results because those kids haven't taken out some time to master English and sports. And so you may end up with a kid who is able to show, for example, that sine square x plus cos square x equal 1, but can't tell you the past tense of it. Now it's clear that to readjust this situation, the kids have to be taught all the subjects such that there is the balance that these kids need. And obviously this balance will come in a way that the kids now perform better in these 2 subjects, and because they have had part of the time they used to study maths allocated for English and sports, they may perform slightly less than before in maths, but at least what's important to notice this time around, they can now express themselves better in English or practice some sports. Let's now take this other example. Supposing we're training a model which predicts the presence of a car in an image, and then you feed your model with this kind of data. Then after training your model, where you get to test that model is on this kind of real world data. It's clear that even if you had very great results with the previous data, in this or working with this or testing on this new data set right here, you wouldn't have those amazing results you had previously. And so it's important that not only should your data be large enough or gather as much useful data as you can, but ensure that your training data represents or looks like your test data or looks like what you're gonna be having in production, as that's really what matters. What matters is the fact that you have a model in production which works well or which has high accuracy, and not a model in your notebook which has, say, 100% accuracy on your trained data, whereas on production it doesn't perform very well. Now moving on to underfitting, it turns out that here our model becomes way too simple for it to even be able to extract information from our data. So we may have our validation data and then our training data like this, and then there is this huge gap between our current loss and the minimum possible loss. We could also have this at the level of let's say accuracy. So here we could have accuracy, and then we have our validation, and then training, and we have, say, accuracy 100%. Let's say we have 1 right here, and then our model is still too simple that we just end up, say, at 0.6 or 60% accuracy. In this kind of situation, our data, or the relative size of our data as compared to the model, may be too large. So you could even have a situation where this data is smaller than what we had here. So your data could be small like this, but if your model is way too simple, say we have just this very small model, then you may
face this problem of underfitting. It also turns out that sometimes you may have a situation where you have even a very complex model, but that model still underfits. And that's because that model hasn't been built in a way that it could extract useful information from this data. Now, if you could recall in the section where we're predicting the car price, we had a situation where a model, we use a simple dense layer. We use a simple single dense layer with just two parameters, and we had this fixed data set. But once we increased or stacked up more dense layers, we found out that we're able to get better training and validation mean average error values. There are several ways in which we could mitigate this problem of overfitting. The very first one we'll look at is that of collecting more data. So it's important to lay hands on as much data as you can. This data has to be representative of what the model would see in real life, and this data should be as diverse as possible. Even after collecting more data, to solve this problem of overfitting, we could use data augmentation. Now, what is data augmentation all about? Supposing we have this image cell right here, the cell image we have here, which happens to be parasitized. Now, instead of having just this in our data set, we could have this image right here modified such that we now have more data to train on. So this means that in the case where initially we had, say, 20,000 images, so we have 20,000 images. Now, after doing data augmentation, after modifying each and every image, we now have a data set of 80,000. Now, we're considering 80,000 because we're supposing that each image is going to be flipped as we've just done right here. So we take this image, we rotate it, we have this other image, the same level, obviously, still parasitized. And then we flip again and get this image. We flip, get this image, flip, get this image. We see that we now have, instead of just this one, we have 4 others. This actually means, we're multiplying this by 5. So this is 100,000, since we have it now 1, 2, 3, 4, 5 examples for this single example we had initially. It should also be noted that there are many other data augmentation strategies for this kind of image data. So apart from flipping as we've just done, we could crop just a portion, we could add some noise to this data, we could modify the contrast, we could modify the brightness, and carry out so many other operations. And there is no particular data augmentation strategy which works for all problems. This means that when you have a particular problem, you will have to try different augmentation strategies and then be able to select the one which works for your data. Now, that said, we have dropout. To better understand this notion of dropout, we'll consider this simple neural network right here. Now, if you could recall, the reason why we have models which overfit is because we are working with very complex models with many parameters. Now, in order to reduce the complexity of this neural network, what we could do is take off, for example, this interaction between this neuron and all these previous neurons right here. So this means that when training our model, we are only going to consider that we have in this hidden layer just these 2 neurons right here. So all those connections here become useless. Now, this has the effect of simplifying our network, as what we have as output now, that's after carrying out the dropout operation, looks like this. So we have now connections which look like this. Now, this particular case is an example of a dropout with dropout ratio equal 0.3, or let's say 0.333, as we're dropping out exactly 1/3 of all the connections, or rather 1/3 of all our neurons right here. And if r equal to 1/3, what we'll be left with will be this. So we'll take this off and we'll be left just with this neural network to train right here. We see that we could leave from this very complex model to a simplified model via this dropout operation, and this has an overall effect of mitigating overfitting. The next step we could take is that of regularization. To better understand regularization, suppose we have this model with weights wj. So we have say n weights, and these weights are free to take up any value. As we've seen previously, the fact that these weights can take up just any value may lead to overfitting, as now these weights can be adjusted to fit on the training data in a very perfect manner. So this means that we could have a model which picks out each and every point like this. So we have this kind of model, and we have this. So we have this model which picks up every point like that. Whereas if we restrain these weights to stay in a given range, then we may end up with something like this. So we may end up with a model which looks simplified like this, because it doesn't have as much freedom as this other model. Now the problem with this model is, if now you put in this new data, you'll find that this one will try to pull out like this, and then your prediction will be somewhere around here. And so if, for example, we're having horsepower on the x-axis, and then here we want to predict the price of a car, let's do same here. We have the price and then the horsepower. Then it happens that we have this car with this very high horsepower. This model, because it is overfitted on this training data, will predict this very low price, whereas this model, which is generalized on this training data, will tend to predict a more reasonable price. Now, it should be noted here that because this model was able to go through each and every point, we would have a training loss of almost zero. Whereas now when we give it this new data, it doesn't perform well. Whereas with this, we wouldn't have a training loss of zero, but when given new data, at least we're gonna have reasonable predictions. So coming back to regularization, our aim is to ensure that this weights, because this model can be represented as this function, and this function is made of this weights. And so since when we're doing training, our aim is to ensure that we minimize the loss, then we could include this weights in the computation of the loss. This means that we have our loss, which is now equal the loss we would have normally, plus this regularization constant times the sum of this weights of each and every weight square. Now this is known as L2 regularization, whereas here we have L1 regularization, where we're summing up the absolute value of each and every weight. For now, we're just gonna explain how regularization helps in mitigating that problem of overfitting by restraining those weights in a given range. So let's have here loss equal L, that's initial loss, plus let's call this R. Now if our aim is to minimize this loss, then obviously this L will be minimized and the R will be minimized. And so if we're trying to minimize this here, or this sum in general, then it would have that overall effect of restraining these weights in a given range. Especially as we know that when we square very large values, these values become even larger. And so to avoid this, our weights will tend to take up smaller values which fall under a smaller range. This L2 regularization is also known as weight decay. It should be noted that the main difference between this L2 regularization and the L1 regularization is that in trying to restrain the range of values which these weights can take up, the L1 regularization has that negative effect of making many of those weights to take up values around 0. That's values very, very small, or take up many 0 values. So this will lead to sparse models as compared to the L2 regularization. And that's why in practice we generally use the L2 regularization. That said, we move on to Ltopping, which we've seen already. In Ltopping, as we have seen, if we have our model, let's say we have precision, validation precision, and then the training precision, which keeps on increasing, and then we have this limit here of 1 or 100%. So we have the precision and we have our epochs, and then after a while this starts dropping, and this starts dropping simply because our model is now trying to overfit on this data it's been trained on. And so we have to stop training once we notice that the validation performance isn't improving any longer. So this means that after a certain number of epochs, we are going to stop the training. And we've seen this already in the previous section. We've seen it both theoretically like this, and then we had seen it practically. Then another thing to do is to reduce the size of the network or use a less complex network. Our next step will be to properly tune our hyperparameters. Hyperparameters like batch size, dropout rate, regularization rate, and the learning rate can affect our model and dictate whether this model will overfit or not. Now, if we look at the batch size, training with a larger batch size may speed up our training process, but working with smaller batch sizes have a regularization effect which help reduce overfitting. And so, according to Yann LeCun, friends don't let friends use mini batches larger than 32. For the dropout rate, we've seen this already. Increasing the dropout rate means we are making the model simpler, and the regularization rate, increasing the regularization rate means we're reducing the effect of overfitting. And then finally, picking too small of a learning rate may lead to overfitting. So in general, we have some hyperparameters to tune, and they are not only limited to this, as you may have many other hyperparameters depending on your problem. Now, the fact that normalization introduces extra parameters mu sigma, which bring in some noise in the model, has that regularization effect which help reduce overfitting. So if you're including batch norm in your model, then you could feel free to reduce the dropout rate, since this normalization layer already brings in that regularization effect. From here, we look at ways of mitigating the problem of underfitting. So with underfitting, we could use more complex models. We could also collect more data. We see that this solution falls in the two, that's both overfitting and underfitting. Here is always a good thing to collect more data or more clean and representative data. So from here we have, you could also improve the training time. Now note that you could have this model, like let's take this, and then we have here you've trained, and then you have the validation. So here you have the val, and then you have the train, and then you've been training for over say 1,000 epochs, and then you feel like the model may not perform any better. Now, several scientists have reported that many times they've given up on a model and then come back later after forgetting to stop the training process and notice that this model kept on performing much better. So sometimes you don't have to give up on your model. So you could train, or you could increase this training time. Then again, we have hyperparameter tuning, which could help in making your model more performant. And we have normalization, which stabilizes the training process and leads to better performance in the model. We now see practically how the dropout could be implemented with TensorFlow. So here we have this dropout layer, which takes as argument the rate the dropout rate, noise shape, and the seeding. To better understand how and why we need to use seeding is simply in the case where we want a reproducible experiment. So if we want to apply dropout in this layer with a dropout rate of 0.2, then we'll be taking off 1 neuron out of this 5 neurons to make our model simpler and avoid overfitting. Now in doing so, we may take this one or this or this one or this or this other one. So it's a random choice. Now if we want to fix this choice so that this experiment can be reproducible, then we can set this seed so that each time we run the experiment, it's going to be exactly the same neuron which is going to be taken off. Getting back to the code, the way we could use this is by importing the dropout layer. So here we just have this dropout, we run that and it's fine. And then we could include this dropout right here. So we could have here dropout, let's say dropout rate equal 0.2. Now you could always increase this rate. So let's have that, and then we have the dropout, and then dropout, or rather rate equal dropout rate. That's fine. We could paste this out here, but wouldn't want to add dropout here. Anyway, you could always include the dropout at this level depending on how the model responds to this dropout which has been added here. So let's add this dropout and then add the dropout right here. Bearing in mind that we could always add more dropout layers and increase the dropout rate or even reduce this rate. So that's fine. We run our model, and as you could see right here, this dropout has no parameters. From this, we look at regularizers. We'll see how to implement the L2 regularizer and the L1 regularizer. So here we have TF Keras, and then we have this regularizers right here. So if you select L2, you should fall on this page. Now, once you get this, you see you have this TF.Keras, the regularizers, L2, and then you specify the regularization rate. So let's copy this out and then get back to our model. At the level of our model, let's come back to the definition of the conv2d. So here we had this kernel regularizer, and it's this kernel regularizer that we use in carrying out regularization. So here we have this conv2d, and then we simply specify the kernel regularizer. We have kernel regularizer, which is equal this regularizer right here. Now let's take this off, and there we go. We have this kernel regularizer, which is now our L2 regularizer. You could always take this off, and then from here, and you have from TensorFlow.Keras.Regularizers import L2. So that's it. You could also import L1. So run that. Let's correct that. That's regularizer. Okay, so that's fine. We get back to our model right here, and then we have just L2. Now you could have this taken off from here, and then you add it out here. So pattern invalid, activation relu, and that. Okay, so we have this, and then we add our regularizer, and that's fine. Now you could also do this for the dense layers. So just right here, you could have kernel regularizer, and that should be fine. So this is how we implement the weight decay with TensorFlow. Now you could always modify these parameters. So let's have decay or regularization rate 0.01. So that's it. And then we will run our model. That should be fine, and we could go ahead and retrain this model.
That's it for this section. Thank you for getting up to this point, and see you next.